Okay, welcome to Zane State College Physics 2010, Chapter 8. We are going to talk about rotational motion. So, I frequently use an analogy in class in that this rotational motion is like a different language. So we've talked about motion before. We've talked about one and two-dimensional motion earlier in the semester, and we had a bunch of equations for projectile motion and constant acceleration and things like that. And in this chapter, we're going to look at a lot of the same concepts, but because our motion is occurring in a circular path rather than a straight line, or in the case of projectile motions, a parabola, we have to basically translate what we've learned before into this new language. It's like translating English into Spanish or something like that. So we're going to introduce some new terms, some of which, like this, theta, is not really new. We're just using it maybe in a slightly new context. So we talked earlier about using theta when we were talking about vectors, describing the angle that a vector makes with the horizontal axis. And in this case, we're talking about theta is just the amount of measured in radians that the object has rotated. So it's used to describe how much rotation is occurring with our rotational motion. And there's a relationship between theta, the angle, and r, the radius, and this L, arc length. And that relationship is that theta is equal to the arc length divided by the radius. So theta equals L over R, and we can rearrange this equation a couple different ways. We could say R is equal to L over theta, or we could solve it for L. L is equal to theta times R. So that kind of lays the groundwork for our rotational motion. We have some object here that's going to rotate about an axis or point of rotation, and we describe how much it rotates with theta, and we relate the distance arc length L and radius with this equation right here. So if theta is how far something rotates, then this next variable, omega, is how quickly it rotates. We're going to use omega to describe angular velocity. So we're going to use this word angular to describe this rotational motion, since theta describes an angle. How much does the object rotate? What is its angle? So displacement in this rotational or angular type of motion is just simply the final position minus the initial position. You may begin to notice some similarities already between this angular and linear motion when we said delta x is equal to x2 minus x1. So theta is basically the new x in terms of describing position or displacement. And now instead of using a v for velocity, we are going to use omega. Omega is equal to change in theta over change in time. And this image up here is of a character named Omega. So I'd like to tell students to remember the actual Greek letter names. Because I know a lot of times students think, oh, that W thing, that squiggly looking W. But if you think of it as W, you might get it confused with something else that actually is a W. And this is not. This is omega. So you need to think of it as such. And just like with linear velocity, we have average that's what the bar over indicates, average velocity, and instantaneous angular velocity, which is equal to delta theta over delta t, the limit of that as delta t approaches 0. So this is really more of just a conceptual thing to understand that at any one given point in time, if we look at a small enough period of time, we can describe the velocity at that instant, versus the average angular velocity is measured over a significantly larger period of time. Yes, that is omega. Okay, and then if we wanted to change our angular velocity, it would be accelerating. So before, where we used a, when we're talking linear motion, we just simply used an a. Here we're going to use an alpha. And this again is important. This is where it's really more important, because I don't know that we do have any other quantities that are abbreviated with a W, but we do have a and alpha. And so we definitely want to think of this as alpha, not as just a funny looking A. Because if we think of this as an A, then we can get it confused with the actual linear acceleration A. And these are two different things. They're similar, but they are different. So you should really think of this as alpha. And alpha is equal to the change in velocity, the change in omega, the angular velocity, omega 2 minus omega 1, divided by our change in time. So delta omega over delta t equals average alpha. And if we look at the limit as delta t approaches 0 of delta omega over delta t, that will give us the instantaneous acceleration alpha. So now that we've established some new variables or abbreviations that we are going to use to describe our angular displacement, that's theta, velocity, that's omega, and acceleration, that's alpha, we can now start looking at the relationship between angular motion and linear motion. So let's consider this image here where we have this point P that is rotating around and around in a circle. At any point in time, for instance, let's imagine that this is a ball connected to a string that we're spinning around and around and around. If we were to suddenly snap that string, and there was no longer a force holding it in the circular path, this point P would begin to travel in a straight line. And so it would have a linear velocity. And if we want to know how that linear velocity can be determined based on the properties of its rotational motion, we can use this equation here that tells us that the velocity, and this is linear velocity, equals the radius times omega, which is an angular quantity, an angular velocity. So all we need to do is take our angular velocity omega and multiply it by the radius, and that tells us the linear velocity. So we can see from this that if we wanted to increase the linear velocity of a object that is rotating about a point, we could increase the radius. So this point B, which has a larger radius B, is going to have a larger linear velocity compared to point A. So when you're riding on a carousel, if you're on the outside of the circle, you actually have a faster linear velocity. In addition to the linear velocity of the rotating object, we can also look at the what we call tangential linear acceleration. So if the rotational velocity were to change, if we had some delta omega, a change in velocity over a change in time, that would result in alpha, a change in angular acceleration. And as the object accelerates in the angular direction, it will also be experiencing a tangential linear acceleration. So this is just our delta v over delta t, like our linear acceleration that we talked about earlier. So our tangential acceleration, as I said, is change in velocity over change in time. We can do a little bit of substitution here, since we know that velocity is equal to r times omega. We'll take that r times omega and plug it in place of delta v, and we get an r and omega here over t. And then if we look at these two variables, delta omega over delta t, well, we said earlier that that is alpha. That's our angular acceleration. So the way we can relate linear acceleration to angular acceleration is a, and we can put the tangential subscript there to remind us that we're talking about tangential acceleration as opposed to centripetal acceleration. That's equal to the radius times the angular acceleration, alpha. And as I just mentioned, the other kind of acceleration that we use an A to describe is the centripetal acceleration, which we give a subscript of r. Centripetal acceleration is what happens when the object is rotating around this circle. And even if it's rotating with a constant angular velocity, omega, it's still changing direction. And because velocity is a vector quantity, it has both magnitude and direction, if the direction is changing, then that means the velocity is changing. And if the velocity is changing, that means you have an acceleration. And so the acceleration, the centripetal acceleration, the direction of it is from that point towards the center of rotation. So centripetal acceleration can cause a centripetal force. You could think of this, again, if we thought of a ball on a string being spun around and around in a circle, the tension in that string is equal to the force caused by this centripetal acceleration. Or if we think of the moon orbiting the Earth, it is held in place in its orbit by gravity. That gravitational force is a result of acceleration, centripetal acceleration, or perhaps the other way around. The centripetal acceleration is caused by the gravitational force. So centripetal acceleration is equal to velocity squared over r, v squared over r, and v, velocity, is equal to r times omega, so we can substitute that here in this place. And if we square both of these terms on top, we end up with r squared omega squared over r, and then the r and the squared cancel out, and we end up with this, omega squared times r. So that's another way, another formula that we can use to equate centripetal acceleration with angular velocity. So just to recap, here are all of our relationships between linear and angular quantities. So I'm going to end this video here, and we'll talk a little bit more about this slide at the start of the next video.